Hello everyone, welcome to the NPTEL course on Mathematical Foundations of Machine Learning. Let's begin the first lecture. So you have seen that in today's era, machines have started thinking. It's a ethical and philosophical question whether it's a good thing or a bad thing that they have started thinking. Nevertheless, they have started thinking. Now, without going into the ethical and the philosophical issues of learning machines in this particular course, we will look at algorithms which would make these machines think. Now, this is a series of two courses, of which this course that you are a part of currently is the first one. So, here we will build the fundamentals that are required to build the state of the art generative models or even machine learning models. In the next course, subsequent course that would be taught in the next semester, we will be looking at the state of the art algorithms. Now, think of it more like the foundational laying course, where we will look at the probabilistic foundations of what does it mean to make a machine learn. Most of these are English terms, right? Machine is learning, thinking and all this. So, we will have to put some rigor to it by writing equations. Now, in my world, mathematics is nothing less or more than a language. The problem with colloquial languages such as English or whatever is that they are too fragile. You can interpret the language in 100 different ways and there is so much of ambiguity and so on. But for a practitioner who is an engineer, if you want to implement stuff and make something work, ambiguity does not work. So, you need to make things more precise. And to make it precise, you need a language which is designed for precision, and that is mathematics. Now, most of you have studied or rather studying a course on probability theory. When you study the first course on probability theory, most of the results that are taught there seem very strange, right? So, there are things like conditional expectations, law of large numbers and so on. One question that often comes to one's mind is, what is the use of all these algorithms? Right? What are the use? What's the point in even looking at convergence of random variables or transformations of random variables, functions of random variables and so on? It turns out that without those tools, so you cannot make a GPT or a Gemini or large language models work. And in this course, which is a two-part series, at the end of this course, you will start appreciating why these algorithms are important, why one has to talk in a precise mathematical language, and how do you implement all these. And hopefully by the end of the second course, you would also be in a situation where you can develop some of these algorithms. Okay. So, now the objective of this course, the entire objective of this course is to differentiate the learners of this course from what I would call an internet data scientist, right? Now, everybody and their grandmother is a data scientist nowadays. But now, what differentiates somebody, one analogy that is often given is that, of course, you do not need to know how an internal combustion engine works to drive a car, but you need to know the inner workings if you want to build one. And if you want to build one that is more efficient, right, and that is more faster, that is more lucrative in any sense. So, that is the objective of this course. So, at the end of these two courses, students should be in a position where you pick up any of the literature, the state of the art literature from machine learning, you should be in a position to understand what is happening there. Most of the times what happens is, students or people or practitioners get intimidated when they read papers because there is lots of theorems, a lot of math and a lot of jargons and so on. So, the entire objective of this course, one of the objectives of this course is to demystify all that and make you read those papers as you read a novel, right? I mean with ease, that is what I mean. And in my experience this has happened. You can ask the previous takers of the course, and this has happened. The course is designed that way. So initially, as I said, in this first course we will lay the foundation, and I will try to make this course self-contained as much as possible. Right? It will be self-contained, but of course some of the deeper nuances and the research aspects of machine learning will only be discussed in the next course, because it cannot be fit in one full course. That is the objective. Okay, so having said that, let us start. And as I said, I will not use any slides in this course. This will mostly be board work, because you can ask any language model to actually create slides. So now that the course is being recorded, you can put it in a language model and ask it to create slides, and it would do it. What if there is some juice that is left with humanity? It is with things like I can actually write, make mistakes, correct them, and go back, and so on, right? So we will do that. So it will mostly be board work. That's what we will look at. Okay, so now let's look at machine learning and some definitions. And the other thing that I would be doing is, this course would mostly be looking at the algorithms from a probabilistic standpoint. This course will mostly be looking at the ML algorithms from a probabilistic standpoint. I will elaborate on this, and you will be able to appreciate and understand what I mean when I say it's probabilistic standpoint. Now all of you have dealt with the problem of function approximation, right? Most problems in science and engineering can be looked into as function approximation. So what is function approximation? From the time of people like Kepler and Gauss and so on, they have been asking this question of function approximation. And one famous problem that bogged a lot of mathematicians in early 16th, 17th, 18th century is to find a function that would estimate the positions of planet, right? So they observed the positions of planets at different points in time. They wanted to know where these planets are going to be in some other points in time where the observations are not made. Okay, so this mathematically can be formulated as a function approximation problem. So what is a function approximation problem? You have two sets, call that X, this is the domain set, so fashionably also called as the input. We will not use the word input because it's at an abstraction level, it's just a random variable. We will come to that in a while. For now, it's elements of some set, call it domain set. And there is one other set that we call the range set. You can roughly call that as an output. So what is given are pairs or tuples of this sort. So let us call this another set where you have points of this sort. I have x1 comma y1 and x2 comma y2 till xn. Let's rather use the uppercase here. Where xi comma yi is a pair of observations. Now what is happening is that you are given n pairs of observation xi comma yi, where you can simply at a mathematical abstraction level, you can simply look into this as elements from two different sets. For every xi, you have a corresponding yi. Now we assume, so we make an assumption, assume that there exists, so this symbol stands for there exists a function f assuming that all of you know what a function is, right? A function is a mapping between two sets x and y. So from set x to y. So what does it do? Given a particular xi, it will give you the corresponding yi. It will operate on an element of x, script x, and it will give you a yi, and there exists a function. The whole problem is that the underlying function f is unknown. The whole problem is this. So we are assuming that there exists a mapping between the input set and the output set, or the domain and range, while we have observations, right, which are evaluations of the function, which we represented by this set D. We do not know what the underlying function is. Okay. So now given this, so given D, find f. So this has been a classical problem in science and engineering, right. So there some underlying function exists, we do not know what the function is. However, we have observations from that function, so which means that there is an independent variable and a function acts on that independent variable and gives some dependent variable, and we have pairs of these values. So given these pairs, we would want to estimate what the underlying function is. As I said, this has been a problem that is sort of being studied, well studied for years together, right, in different contexts of science and engineering. And one example that I gave is that given that I know the positions of the planet at different points in time, I would want to estimate what would be the location or the position of the planet in some other point in time. So in this case, your time can be seen as x and the positions can be seen as y, and so on. So you can look at multiple examples. Now, how are people solving this problem? If you look at historically, see, one way to solve this, first of all, can we solve this problem? So it's actually, it's an ill-posed problem or a blind problem, because we know nothing about f. The underlying function that connects the time to the position of a planet is completely unknown while you are making the observations. Now, when you have no information about the underlying function, but only given observations from that function, how do you estimate the underlying function is the question. How do you do that? If you are totally blind, how do you solve that problem? Anybody?
Just define the function at those points to be the values, not preserve that.
Well, that's a bad way to do it, right? I mean, the one suggestion is that you just define the function to be equal to yi's at every point in xi, but that's not a good estimate, because see, the whole point, why do we want to find the function in the very first place? We want to find the function because we need to know what the output of that function is for x that we have not observed. Now, if you define your function to be equal to the values that it has taken at all observed points, then there is no, I mean, that does not serve our purpose. In fact, we will, nice that you put this idea out, because we will formalize this idea. This is what is called as overfitting, right? We will see that idea later in the course, we will formalize that idea. So we do not want such an approximation, but I am asking you for the, the high level philosophy or idea of how do you solve a problem if you are not given anything, you are completely blind in a scenario. In this case, how are you going to solve this problem? Yeah, but you have to start from somewhere, right? What do you optimize on? See, optimization etc. comes later. The first thing that you should start with is yeah, see, we have not even discussed about what is an idea of error. See, this is exactly the point that I am trying to make. We have some idea of how to solve problems, but we don't have the precise idea of how to solve problems. So this is the gap that I am trying to fill in this particular course. So optimize, error minimization, all that is fine. So now what is optimization? What's the notion of error? Right? This is what we are going to define as we move on in the course. But at a philosophical level, so what you should do is that in these kinds of situations, okay, so start with some initial guess on f. So, you first start with some guess on f, okay. Just say that fine, I mean I make an assumption that my f, the underlying function, is a parabola. This is one example. In fact, people like Kepler actually did that. They said that planetary path is an ellipse. So, you make an assumption that it is an ellipse. Now, given that I have made an assumption that this is an ellipse, now what is the question that I need to answer? So, have I answered the entire question? I have not. Why? I have already told you that it is an ellipse. So, what else remains? I will have to tell you which ellipse is it. So, there can exist infinite ellipses. So, given that I have made an assumption that my reality is an ellipse, now tell me amongst infinite possible choices that I can have for I mean infinite ellipses that I can choose from, which ellipse should I choose in this particular situation? So, this is the question that we will be answering. Now, every estimate that you make for f is called a model. Okay. There is a colloquial saying, proverbial saying in machine learning community which says that all models are wrong, but some are useful, right. So, our objective, right, is to get a useful model. So, now we will define the notion of what useful is. Now, one thing that I want all of you to understand is that every estimate that we get for this f is a model, is an estimate, right. So, we have no access to reality. We have no access to what was the underlying function that actually generated this sort of data. So, we will only get an estimate. So, now the idea is start with some initial guess on f and refine the guess using D. So, this set D, which are the observations that we have, is what is often referred to as data. And you people have already heard this, that data is the new oil, right. We will see later that why that statement is not an overstatement and why the quality of your data determines how good your f is and so on, right. So, this is the philosophy. So, what happened is that we are given some pairs of observations, one from two sets basically, and we assume that there exists a mapping between these two sets. One is called the domain, the other is the range. If you want to call it input output, call it input output, two sets mapping given the observations made from that particular function. The objective is to estimate the underlying function, okay. The way to do it is start with some initial guess on f and then refine the guess using the data. Now, I have told you what we will be doing in this entire course in a nutshell. Now, the questions that we will be asking is what guess to make, okay, and how to refine this guess using data, and how do we know whether the guess that we have made or the refinement procedure that we have resorted to is a good refinement procedure. So, there are 10 ways to do it, 100 ways to do it. Every refinement procedure is an algorithm, and every guess that we do is a model, is a model family. So, there is linear models, linear family of models, and there are quadratic family of models, and there are kernel machines, and there are neural networks. All of these, there are decision trees. All of these are the guesses, the initial guesses that we make on f, right. And there are algorithms to refine the guess that we make, and these algorithms will give rise to a machine learning method basically. So, one is the error backpropagation. The error backpropagation is an algorithm that is used to do this refinement on a family of models called neural networks, which we will be seeing, and so on. So, depending upon what sort of model choice that we make, the algorithm, the refinement algorithm will change, and that is what we call as learning. We will formalize all these ideas as we move on. So, at a broad level, this is what we are going to do in this course. Okay. Now, when I started, I told you that we will be looking at the probabilistic viewpoint. So, what do I mean by that? So this is very important. So today we will actually look at this. So people often don't appreciate why one would need probabilistic viewpoint. See, while whatever I said so far, or rather the entire machine, or rather most of the machine learning algorithms can be explained away from the deterministic viewpoint that I just told you, there are things that would not fit well if you do not have the probabilistic viewpoint. See, for instance, generative models. Generative models are best explained from a probabilistic standpoint. Okay, and probabilistic standpoint is so general enough that it can encompass both the discriminative and generative framework. We will formally define those terminologies as we move on. But yeah, so probabilistic framework is more broader in the sense that it will encompass all kinds of formulations of machine learning. So that's one way to look at it. The other way to look at it is as follows. Think about it. Now let's say that the problem that we are looking at is that you are given a picture, okay, or an X-ray. All of you understand what an X-ray is, right? An X-ray image of somebody's lungs, and you are also given the outputs or the Y set of it. I mean the elements from the Y set or the range set, which would tell you whether this particular X-ray has a particular type of disease or not. Okay. In this case, let us write that down. Now consider X-rays to be X-ray images. Now note that when I said that I am looking at functions, there is a domain and there is a range. I did not restrict the elements of this domain and range, right. So now the elements, each element of this set X can be a vector. What do I mean by that? I am talking of vector valued functions. So all of you understand what a vector valued function is, right? A function that would take a vector as an input and gives a vector as an output. And scalar is also a special vector, all of you know that, right. So I did not restrict these X to be scalars. Now in the case of X-ray, you imagine each of the X-ray image as a vector. I will tell you how to imagine each of an X-ray as a vector. So now for abstraction sake, let us say that each of these X-rays is a vector. Okay. Now what do I have is that I have X-rays as my X-rays, and okay, so maybe I will just concretize it right away so that you have a better image of what I am saying. So this is an image, right, an X-ray image. What is an X-ray image? Hold on. Okay, so now this is an X-ray image. So what we have P pixels here and Q pixels here. So what is a pixel? When you represent an image in a computer, in a digital system, what you get is a matrix, right. So each of the elements of this matrix is a number between 0 and 255 if you are looking at an 8-bit image. Okay. Now I have P times Q number of pixels, each of which can take a value between 0 and 255. Does it make sense? That is what an image is. Now what I do is I will stack each of these numbers along the columns. I take the first column, okay, this is the first column. I take the second column of the image and keep stacking it. Okay, and how many columns are there? There are P columns, Pth column. I stack them all, and now this becomes a large vector. And what would be the size of this vector? PQ. The size of this vector is PQ, right? PQ sized vector. You have a PQ sized vector. Okay. Mathematically speaking, I can say that this is a point in a RPQ dimensional space. So now this is a visualization that I want all of you to have right now, that our data or every element of this X set that we are talking about is a point in a very high dimensional, or rather in a high dimensional Euclidean space. So for people who want their memories to be refreshed, a Euclidean space is an extension of the two-dimensional Cartesian plane. In a two-dimensional Cartesian plane you have two numbers, in three dimension you have three numbers, in n dimension you have, as human beings we can't visualize anything beyond three dimensions of course, but this is a point in some PQ dimensional space. I will generalize that going forward and say that my every xi in the set that I have is actually a point in some d dimensional Euclidean space. This is the notation that I will be using. An element in the set X, which is my input set, is a vector in a d dimensional real space. I am assuming that all the data that we have, all of them are real valued. Does that make sense? Okay, yeah. So this is for so we were looking at why do we need a probabilistic viewpoint. Let's get back there. Now let's say that xi's are these d dimensional images that we have, and yi, okay, is simply one of two possibilities, 0 and 1, okay, where 0 is diseased and 1 is benign, right, or you want to say non-diseased. Okay. Now we are dealing with a problem. So there exists an f, okay, that would take elements of x and projects it to space y. So now note that what is this function f doing? This function is looking at a point in d dimensional space, or PQ, I mean our PQ is here d, right, it is taking a point at d dimensional space and assigning it a value of either 0 or 1. Does that make sense? Right. In fact, in real world this function f is a pathologist or a radiologist. He or she is looking at the images, these X-rays, and diagnosing whether this X-ray correspond to a disease case or a non-disease case. Make sense? Now given that somebody has given us some 1000 X-rays with these labels, the problem is to find a function f, okay, or mimic this radiologist. So you might have heard, right, everybody will be out of job, this is what they mean. So we started by learning what a clinician or a radiologist do. At the end of the course we will try to learn a function that would mimic anybody's job. So that is the universal function approximation idea. So basically learn any function, that's how it translates to mathematically speaking, but anyway. So we want to learn this function given 1000 X-rays. So given 1000 X-rays with the corresponding labels, our objective is to learn that underlying function that would look at an image and gives it a label of 0 or 1. So now you interpret it the way you want, I mean you call 0 as disease, 1 as non-disease or anything, basically it is a function approximation problem. Now here is the catch. Now suppose you want to connect, so what is this function doing? This f is actually mapping one observations with the other. Now suppose you want to connect mass with acceleration, both are measurable and we know how to connect them, right, and force, I mean I meant force and acceleration. There is force and acceleration, we know how to connect them. How to connect them? They are linearly dependent, that's it, easy. And suppose you want to connect velocity with acceleration, and we know how to do that, right, because both are measurable. Now what do we want to connect here is the question. Think about it, it is very subtle. Now this x that we have right now, which we call as image, okay, is actually the measurement of how much light, or rather how much radiation that a particular surface is reflecting or absorbing, not observing, absorbing. If you take a picture of some surface, right, what are you actually measuring? If you go at the level of the sensor, what you are actually measuring is the amount of reflectance that the surface that is being measured is offering. Now, why would that correspond to an abstract idea called diseased? Do you see the question? More so, we know that machine learning today can do gender identification looking at images, correct? So, gender is an idea that is very synthetic. Why would the amount of light that somebody's face reflect correspond to a synthetic human created idea called gender? Now, you extend this idea to anything. So, now today's ML, today's machine learning algorithms does speech recognition, intent recognition, right. So, what is a microphone measuring? A microphone is simply measuring the amount of pressure gradient that is being that's being observed in the environment. That is what a condenser microphone will measure. So, why would that correspond to something that is a semantic meaning? You get what I am saying? So, now the problem is that if there are things that are measurable, I keep joking all the time. So, it turns out that learning a function that is useful to even fly an aircraft is easy, because you can actually fly an aircraft using Newtonian mechanics that does not need more than 4 or 5 parameters. But to find out whether somebody's picture is that of a male gender or a female gender, you need a 100 million parameter model. Why? Because human beings are complicated and human constructs are very, very complicated by construction. So, one of the assignments or experiments that I will make you to do is the following, right. So, let us say that we take the pictures of handwritten digits. This is one standard data set that people use, called the MNIST data set. So, where you take pictures of handwritten digits. Now, one experiment that I often ask my students to do is that if you randomly label those data sets, can you learn a machine learning model that would explain that random labeling? Turns out that yes, you can. You will see that during your assignments. Do you see the point? Right. So, the idea of semantics is very, very, very complex and very non-trivial. So, if there are measurable quantities like force, acceleration, mass, etc., then a deterministic worldview is enough. But when you are trying to learn functions between quantities that are not so well defined and very abstract, having a deterministic worldview won't help. I will give you another example. Let us say that the task that I have is that given a coin, okay, I want to predict, or rather I want to predict the outcome of the toss of that coin when I toss it. Can I solve it? So, let us say that I give you the outcome of 100 coin tosses. What are the outcomes? In a coin, there are only 2 possible outcomes. I will give you all the outcomes of the coin toss, and every coin toss I make some 5 measurements. What measurement I will do? So, I will measure what is the mass of that, what is the weight of that coin, and I will measure what is the atmospheric pressure, and I will measure what is the pressure with which the person tossed the coin, and so on. The question is, given that, can you give me a function that would predict what would be the next coin toss? Can you? Perhaps. It depends. It depends on what measurements are you doing, right. Now, historically speaking, what happened, this happened in mid 80s. So, when people used to solve the problem of speech recognition. So, what was the problem of speech recognition is similar, you can see, all of you can see that problem of speech recognition is similar to what we cast right now, right, because what we measure are vectors. What are these vectors? These vectors are speech signals. What are these speech signals? When somebody speaks, there is a microphone that is tacked in and you get a vector of values. What are actually those values? They are the amount of pressure gradient that is occurring when somebody is speaking. So when you speak, you know the physics, right? The air pressure changes and that is what gets captured from the microphone, and you are given that. Now what you need to do is map those pressure differences into an abstract idea called phoneme. So this sound a, e, u or a, b, c, etc. that we say, they are all abstract, right? They are not measurable. And if you measure the pressure difference while I say the sound a and you say the sound a, they are very different. They are two different vectors. Now when they are two different vectors, how do I map those pressure differences to an abstract idea called phoneme was the question that bogged people for a long time. You know how people were solving it? They modeled the entire speech generation process using physics. Okay, they modeled the speech generation process using physics as concatenation of several waveguides. Okay, and they studied the boundary conditions, all the boundary conditions, and they said that if a particular phoneme is perceived, then the constriction that should happen at the vocal folds has to be in a particular way. And for decades, generation of speech scientists studied this problem of inverting the system. Now given the speech signal, go back to those properties of waveguide. So they modeled this entire speech production process as a process of dynamical waveguide. So basically when you say a, there is one sort of constriction that is happening. When you say e, there is other type of constriction happening. So it's like concatenate multiple pipes of different diameters, okay, and blow air through it. Depending upon what sort of constrictions that are there, you get different sounds. If somebody is familiar with playing a flute, you know what I am talking about, right? So that is how they modeled it. So now they modeled the entire recognition problem as an inversion problem, where given that this is the measurement and this is the corresponding phoneme that has been perceived, invert the process and tell me what sort of waveguide gave rise to this particular thing. So this is how speech recognition problem was being studied. Okay, similar thing happened to image recognition, object recognition as well. I mean, looking at an image, you wanted to find whether there is a person here. There is a. See, what is the ultimatum of an image scene understanding problem? That's what today's ML will very easily do, right? Upload a picture, it will tell you, oh, here is a person, here is it does all of this. This was the holy grail of image recognition or image processing engineers for decades. The way they used to do it is, looking at an image, they first used to detect primitive pictures such as edges and lines and image gradients and all that. Then hierarchically construct different objects and then try to do it and so on. So this is basically they are trying to learn this underlying function, right, but doing it this way. Now what happened, I'm giving you this history just to ensure, just to make you appreciate how important it is to look at the probabilistic viewpoint. Okay. Now in mid 1980s or rather late 1980s, correct, 1980s, people from industry, they solved this problem of connected or rather isolated digit recognition, speech recognition using statistical methods. Now what do you mean by statistical methods? We'll see that in great detail later, but the core idea is, don't look at the physics of the problem, just do repeated observations, right, and deduce statistical outcomes from it. If I go back to the example of coin toss that I just told you, I cannot predict, the objective is to predict what the outcome of the coin toss is, right. Now I don't know how to study the physics of the problem, so what I will do is, I will toss this coin 10,000 times, right, and I will count how many of them turned out to be heads, and then I use statistics to answer questions such as, what are the chances of my next toss going to be heads and tails and so on, right. Same thing happened with speech recognition. People used statistical methods to solve the problem of speech recognition, and the joke is, or rather the cruel joke is that people, speech scientists, physicists that were studying the problem of speech recognition from first principle, physics based first principle, called this as ignorance modeling. Because they said, since you don't know what's happening, you are modeling your ignorance in a statistical way. And engineers said, fine, okay, we don't mind, but it works. That's exactly what's happening today. So you don't know what are the the nuts and bolts of the modern day machine learning algorithms are, in the sense that it's very poorly understand what the inner workings of these, other than the engineering nuances of it. We know how to build systems, but we don't know how to understand them. At one philosophical school of argument is, who cares, we don't understand human brain as well, but it works. An engineer would say it that way, right? I mean, yeah, I mean, today machines are thinking, right? We will eventually, maybe we'll understand, but at least they are thinking today. So this is why you need the statistical way of doing it. Long story short, I'll write that now. The thing is, f is complex to be estimated from the physics of the problem. Now, in most of the problems which we call as the thinking problems, you cannot estimate f from the physics of the problem. As I said, the example is, why would the amount of, see, the question that I am asking is, the amount of light that gets reflected from some surface, how is that related to an idea called gender? We don't know. Okay, but what we can definitely do is take a lot of pictures and ask somebody to rate whether, or rather annotate this so as to whether this is a male gender or a female gender, and try to use statistics to build something that works. So that's the whole idea. Okay, so because f, or the underlying function, is complex or difficult to be modeled using the physics of the problem, we need to resort to the statistical methods, where the idea is to do repeated observations. So now resort to statistical methods. Idea is, make repeated observations and estimate f. So this is why we need probability theory. So what is probability theory all about? That we make repeated observations and then try to learn our estimates. Does it make sense? Okay. Now if we do this, then we will have to formulate this problem of function approximation, right? What was our problem? The problem in machine learning is pretty simple, right? Given D, find f. So there are two sets, mappings from one to the other, and there is a function that's mapping one to the other. Given multiple observations from that particular underlying function, you estimate the function. That's all the problem is, right? Now this is from a deterministic standpoint. Now from a probabilistic standpoint, things change now. Now this x and y no longer happen to be deterministic sets, they happen to be random variables. Okay, so now x and y in a probabilistic framework so spaces x and y define, or rather impose, random variables. In fact, to be precise, they are the support set of random variables. What does that mean? all of you have taken a first course in probability would probably know that a random variable is neither random nor a variable. It's a deterministic function. It's a deterministic function from sample space to real values, right? And it's just not a mathematical construct, right? It was not defined that way just for fun, right? And I'm assuming that all of you at least have heard terms like Borel sigma algebra and measure spaces and so on, right? That's the first shock that you get once you come to ISC. But they are very, very needed. So you need a measure which we call as probability measure. So we will end the class here, but I would urge all of you to refresh your probability theory basics when you are coming to the next class, specifically these concepts. The idea of sample space, okay, the idea of what a random experiment is, the idea of a random variable, okay, and the idea of a probability distribution function. Of course, there is a probability measure and then you have a probability distribution function, okay, and of course density functions and so on. Okay, density functions, you know that density functions may or may not exist for all random variables. Please review your probability theory basics very, very thoroughly. What we will do in the next session is that I will connect all these function approximation problem that I just said to the ideas of random variables and the distribution functions. You know, in fact, people who can see can already see this problem of function approximation gets translates to a function of distribution estimation, right? And they have parallels everywhere. They have 1:1 parallels. There are parallels between estimating a function in the deterministic worldview and estimating a density function, or rather the distribution function in the probabilistic framework. They are not yet done. You can wait to pack your bags. So please review your probability theory basics very, very thoroughly, and it is going to get rigorous. Okay. So yeah, so we are going to look at the course from a purely probabilistic standpoint, but I will give you the deterministic equivalence at all points, but the course will be based on the probabilistic framework. So please review what your probability theory fundamentals are while you are coming to the next class. Okay, we will stop here today. Thank you.